nucleotides. We don't really add them. I don't know if you guys remember the difference between a nucleotide and a nucleoside. All of these fun facts coming back to haunt you. But a nucleoside was the sugar plus the nitrogenous base. So that equals a nucleoside. And if we want to turn a nucleoside into a nucleotide, we attach a phosphate. That's the difference between a nucleoside and a nucleotide. We don't actually attach a nucleoside with a single phosphate attached to it. We actually attach a molecule that's a nucleotide or a nucleoside triphosphate. So we take one of these nucleosides, we put 3 phosphates on the end, just like adenosine triphosphate. We attach 3 little phosphates to it, and that's what we're actually going to add into the elongating DNA strand. But what will happen is if you have your, let's call this adenosine, attach it to deoxyribose sugar, so here's our little sugar molecule. And so we'll have these 3 phosphate groups, and basically we'll put this molecule in, we'll attach it to a thymine, and when we do that, these 2 terminal phosphates are going to pop off, and that's called pyrophosphate. But that little cleavage, because this is a really unstable bond when we have these 3 phosphates all negatively charged, all tight together, that's a really unstable structure. And so when you release that tension, it provides some of the energy that we use to drive the DNA synthesis. So that's why we do it. It's not for no reason. So we'll have these nucleoside triphosphates. Again, that's part of the way that we're providing the energy to allow this process to occur. So it's giving you specifically with the ATP molecule. But here's our thymine nucleoside triphosphate, and we basically are going to attach this thymine to the adenine, where these 2 terminal phosphates are going to pop off. They're known as a pyrophosphate. That's, again, just driving the energy, so we end up with a nucleoside monophosphate being added, otherwise known as a Okay, so here we go talking a little bit about where the problem comes into play in the fact that I told you that we'll have these replication bubbles form, and so you'll have one strand up here and one strand down here. One of these strands is fine, it's in the 3' to 5' direction, but the other is going to give us trouble, right? The other's in the wrong direction. So basically, one thing that's going to happen is you're going to have, see, in the 5' to 3' direction, you're going to have replication go, no problem, zoom, I'm off to the races. But what do we do over here when we're trying to go in the 3' to 5' direction? And I've told you we cannot do that. We cannot build that way. So, but we're still elongating in that direction. How are we doing it? And this is where we come up with this idea of going backwards to go forwards. Anybody seen the movie Cars? Go left.
Oh, yeah.
Go left to turn right, or something like that. I get to watch lots of Disney movies. So basically what's going to happen in that direction, so we're trying to go, I told you we can go 5' to 3', no problem. But if we're trying to go 3' to 5', we can't do it. So the way that we're going to have to do it is we're going to have to kind of come like this and still go in the 3' or 5' to 3' direction, but build these short sequences that are kind of run in the correct direction, but fill in the space, so we're going backwards to go forwards, basically. Does that make sense? So these little fragments have a name. Of course they do. The person who identified them are called Exactly fragments. I'll show you them to you in a minute. But that's how we're going to get around the fact that we can't synthesize DNA in the, I have to always think about this now, in the 3' to 5' direction, only in the 5' to 3' direction. You just zoom away. And I have several slides that show some demonstrations of this.
Wait, isn't it to 3' to the 5' or?
Now we can go 5' to 3' direction, because if you think about it, we can only attach, so here's 5' to 3', we can only attach to the 3' end, because there's a little hydroxyl group here.
Oh.
On the 3' to 5' direction, this is a phosphate. We cannot attach anything going 3' to 5'. This is important, like to keep straight, I would draw a little diagram, just to remind yourself. I can only, on the test, because some of these questions will affect your ability to answer the questions correctly. So I'll always think about the fact that I can only go without any trouble, without needing these little Okazaki fragments. I can only go 5' to 3', because I can only attach a new nucleotide to that 3' hydroxyl group.
That's what that line is, a nucleotide. The little line that you keep that's drawn in between?
This would be a strand of DNA,
Oh,
and then the nucleotide is the, adenosine, thymine, guanine, cytosine. I can only attach that to this little 3' hydroxyl in it. So I can only synthesize new DNA in the 5' to 3' direction. But remember, this would be the new strand. So the new strand is based on the template that's 3' to 5', just to make it more confusing. So always anti-parallel. If you have a sequence that's 3' to 5', you can build off of that very easily because you're going in the 5' to 3' direction. If you have a strand that's going the opposite, that's going 5' to 3', and you're trying to make a complementary base pair, you can't just go off to the races and synthesize like that. You would have to now make these little Okazaki fragments and bind them together. Okay? Kind of and that's one of the tougher concepts. That's why I wanted to point it out to you early on. So draw it out a few times and make sure you understand, okay, I can only go in this direction. This is where the whiteboard comes into play when you're studying. Here's a nicer picture of that than my ugly drawings. So here we've got this origin of replication. So we are synthesizing 2 new strands. And basically what we're going to have, the strand that's going in the easy direction, the 5' to 3' direction where there's no trouble, is called the leading strand. And it just starts and it's just like, woo, I'm off to the races. Here it goes. So here's our leading strand. So we'll have 2 leading strands, one here on one of the parent strands and one of the newly synthesized strands over here. Both of these would be going in the 5' to 3' direction. And then here's how we're going to have to build our lagging strand. So the lagging strand is trying to build in the 3' to 5' direction, but it can't. So it has to make these short little sequences in the 5' to 3' direction and then bind them back together. Okay? Does that make sense? All right, that's the hardest concept of today's lecture. So if you can get that, you're good. Everything else is pretty straightforward. But here you're just watching, we've got these little RNA primers. We've got our DNA polymerase attaching new nucleotides. No problem, again, here for this leading strand. It's just a problem for the lagging strand. And this is our DNA polymerase that's kind of jumping off of the RNA primer, and then we'll have another DNA polymerase that will come and take the RNA out and substitute the correct DNA nucleotides in its place. Okay, so that's our leading strand definition. The lagging strand is the one that has to work away from the replication fork and make these little short fragments that are going to be bound together. The fragments, again, are called Okazaki fragments. And they have to, if you think about it, we've got all these little fragments. We've got to connect them. DNA polymerase can't connect them, right? This is the other hardest part of this lecture is that there's a lot of different enzymes that have different jobs. So just getting familiar with what's the enzyme called and what does it do. A lot of them are intuitive, which is always good. So the enzyme that is going to connect or ligate the little strands is called a ligase. To ligate something is to attach it together. So all of these little fragments have to get connected with this enzyme called ligase. DNA polymerase can only do one thing. It can only attach the newly synthesized nucleotides to an existing 3' end. Okay? Can't connect things, can't make a primer. It can also proofread, but we'll get to that in a minute. So here's just an image looking at our lagging strand. So here we are. Here's the 5' to 3' direction. So we need to go in the, normally you would be synthesizing 3' to 5' if you're trying to go from this origin. We can't go 3' to 5'. So we have to make these short fragments that go in the 5' to 3' direction. 5' to 3', 5' to 3'. You'll still need an RNA primer. Remember, DNA polymerase, you're going to have to make a bunch of little primer fragments. For each of the Okazaki fragments have to have their own RNA primer. So RNA primase will have to come in and make a short, 3 or 4 nucleotide primer. Then the DNA polymerase can extend that. And it's showing here it will extend it until it meets the next RNA primer. And then it'll pop off and it'll go back and keep doing its job over and over and over again. It's the nice thing about enzymes. They can continue to do the same work. And then once it pops off, we're going to now have to make a connection here between these two little fragments. So we will use ligase to, actually, before we do that, we have to go take the RNA out, put the DNA in. So that'll happen first. And then once we've replaced the RNA primers with DNA, And this is where it's kind of pointing out, okay, these are some of